Hi, my name is Roland Martinez and I'm here to show you the video documentation or presentation of my project in ECE103L or Electronics 1 Laboratory. And the project is regulated power supply circuit design. And the specification is 6 volts DC regulated power supply, while the input is 220 volts AC input with 60 Hz frequency. To go further, before modeling on the LT-SPICE, I have some design calculation to present. So this is the slide of the design calculation. First, for the rectifier circuit calculation, you can see on the screen the rectifier circuit. This is the schematic diagram or circuit design of the rectifier circuit, which is a 220 volts AC input with 60 Hz frequency. From the primary input voltage, which is the VP or V primary, the voltage is 220 volts AC with 60 Hz frequency. Then traveling to the transformer of step-down transformer from 220 volts to 12 volts AC. On the right side will be the secondary voltage or VS. For the computation, the primary voltage or VRMS is equal to 220 volts. Then the voltage peak for the VRMS is equal to 220 volts times square root of 2, which is 311 volts. Then on the transformer design, which is a 220 volts AC to 12 volts AC step down transformer, the ratio of windings is equal to 26:1. So the VS or the V secondary is equal to V primary times the ratio of winding, which is N1 over N2, is equal to 311 volts times 1 over 26. And the result is 12 volts for the secondary voltage. Then for the secondary voltage peak is equal to 12 volts times square root of 2 is equal to 16.97 volts. Then to find the rectified output voltage, which is here, after the voltage is flowing from the secondary voltage or VS traveling to the two diodes, which is forward bias D2 and D3, the V peak rectified or rectified voltage output is equal to 12 volts minus 2 times the diode voltage of 0.7 for each individual diodes, which is the silicon diode, and the VP rec is equal to 10.6 volts. For the peak inverse voltage will be equal to 12 volts minus the voltage of 0.7 volts on one diode. Then the result will be 11.3 volts. For the peak load voltage is equal to 10.6 volts, which is the VP rec or the VP rectified voltage. To find the average voltage, the formula will be VP rec times 2 over pi, where VP rec is equal to 10.6 volts times 2 over pi, and the result is 6.75 volts. For the filter circuit calculation, you can see on my screen the filter circuit schematic diagram. Notice that I have included a capacitor of 470 microfarads in the circuit design, parallel to the load resistance. To find the Vmax, that is 10.6 volts, and to find the V minimum is equal to 10.6 volts minus the 10% of 10.6, which is 9.54 volts, and that is 1.06 volts for the V minimum. Then to find the V rectified peak to peak is equal to 10.6 minus 9.54 is equal to 1.06. That is the amplitude of the ripples, or the peak to peak ripple created on the after the filtering. So to find the exact amount of the capacitor needed in the rectifier circuit, the formula will be C, or the capacitor, is equal to the load voltage. Capacitor is equal to the load current over the voltage RMS of the rectified voltage times 4 times frequency. Then assuming that the load current is 1 ampere, the equation will be 1 ampere over 10.6 volts times 4 times 60 hertz, and the result is 393 microfarads. For the minimum voltage rating of the capacitor needed, VC rating should be greater than V maximum. So the capacitor voltage rating is equal to V RMS, or the V rectified, times square root of 2 plus the 20% safety margin. Then the equation will be 10.6 volts times square root of 2 plus 20% is equal to 15 volts plus 20% of 15 volts, that is 18 volts. So note that it should be 393 microfarads, but I set 470 microfarads, which is higher than the computed value, to reduce the ripples that is present on the 393 microfarads. So going forward, for the regulator circuit calculation, you can see here on my screen the schematic diagram of the regulator circuit design. For the design, the case here, we have a fixed voltage input and a variable load resistance, but I assume that the load resistance is 1k or 1 kilo ohm. So this is a variable resistance depending on the load or the device that will be connected on the power supply. The Zener diode that I selected is a 1A4735A Zener diode, which is a 6.2 volts breakdown voltage, that is near around 6 volts. Then the PZ max of this Zener diode is 1000 milliwatts or 1 watt, and the IZK is equal to 1 milliamp. Then the Zener test current, according to the data sheet, is IZ is equal to 41 milliamperes. So in this power supply circuit schematic design, the required Zener current will be Imax is equal to 41 milliamps for the IZ plus 10% of the IZ, or 10% times 41 milliamps will be 45.1 milliamps. So the required Zener power rating, or PZ, is equal to the Zener voltage times the Zener current, or Imax, is equal to 6.2 volts times 45.1 milliamps, and that is 279.62 milliwatts. And according to the datasheet of the Zener diode, the PZ is equal to 1000 milliwatts, or the safety margin of the Zener diode. So to find the resistor, or the current limiting resistor, or RS will be equal to the V input, the voltage coming from the capacitor, minus the Zener voltage over the max current, and that is 10.6 volts minus 6.2 over 45.1 milliamps, and the result is 97.56 ohms. And to find the max load resistance, the equation will be RL is equal to inner diode voltage over the max current is equal to 6.2 volts, and the Zener max current, which is 45.1 milliamps, equal to 137.47 ohms. And to find the power rating of the series pass resistor, the resistor power rating will be PRS is equal to VL minus VZ, then multiplied by the max current of the Zener diode, and that will be 10.6 volts minus 6.2 volts, then the difference is multiplied by 45.1 milliamps, and that is 198.5 milliwatts. The Zener voltage will be operating at the minimum load resistance, and to find the minimum load resistance, the equation will be RL min is equal to the Zener voltage times the current limiting resistor or resistance over the V input or voltage input minus the Zener voltage, and that is 6.2 volts times 97.56 ohms over 10.6 volts minus 6.2 volts, and the result is 137.5 ohms. To find the max current of the load, the equation will be VZ over RL minimum, and that is 6.2 volts over 137.5 ohms, and the result is 45.1 milliamps. And to find the max Zener current, the equation is IZ max is equal to PZ max over the VZ, and that is 1000 milliwatts over 6.2 volts, and the result is equal to 161.29 milliamps. And the Zener voltage still operates at the maximum load resistance. To find the current at the current limiting resistor, IRS is equal to the voltage input minus the Zener voltage over the current limiting resistance, and that is 10.6 volts minus 6.2 volts over 97.56 ohms, and the result is 45.1 milliamps. And to find the minimum current of the load, the equation is IL min is equal to IZ max minus the current on the current limiting resistance, and that is 161.29 milliamperes minus 45.1 milliamperes, and the result is 116.19 milliamperes. And to find the RL max, or the load resistance or maximum load resistance, the equation is RL max is equal to Zener voltage over the minimum load current, and that is 6.2 volts over 116.19 milliamps, and the result is 5.3 kilo ohms. And the Zener diode will operate within this range, or within 131.5 ohms to 5.3 kilo ohms. To continue, the LT SPICE circuit schematic diagram, or the final schematic diagram of the 6 volts power supply, is presented on the screen. You can see that I use 1N401 rectifier diodes, which is 4 pieces, a capacitor of 470 microfarads with 25 volts voltage rating, and with a current limiting resistor of 97.56 ohms. And the Zener diode that I used is 1N4735A with 1000 milliwatts PZ max, and assuming that the load resistance is 1K, but this is a variable load. Going to the simulation or the LT SPICE environment, note that the actual diode in the LT SPICE library is 1N4148, that is equal to 1N4001, which is not in the library. That makes an error if you run the simulation. The same as with the Zener diode, I use BZX84C6V2L, the same specs as with the 1N4735A. It has a 6.2 breakdown voltage. To compare the result, clicking the simulation button, and going to the graph, clicking D, the graph shows that it is more than 6.3 volts, or approximately 6.5 volts for the regulated DC output. The following will be the components of the power supply: one piece of 1N4735A Zener diode with breakdown voltage of 6.2 volts and a power rating of 1 watt. Then one piece of 220 volts to 12 volts step down AC transformer with current rating of 1 ampere, and 4 pieces of 1N4001 rectifier diode with a 0.7 volts of breakdown voltage, and one piece of 470 microfarads and 25 volts voltage rating of electrolytic capacitor, and one piece of 100 ohm resistor with a power rating of 200 milliwatts. So for the components, you can check the datasheet for the Zener diode, rectifier diode, current limiting resistor, step down AC transformer, and filter capacitor on these links. And for the references,